In this chapter, we're talking about indicators of population health. We'll start with looking at fertility rates and then go to years of potential life lost. We can also look at infant mortality rate as well and get some ideas of what's going on with our population. Let's start with fertility rates. So, general fertility rate is the rate of live births per some number, like per 1,000, in the population of women of reproductive age. That's 15 to 49 years. So, this is a simple calculation. Again, it's a rate because we have a specific time period, like you can do that in a year or something like that. And we add the 1,000 for clarity. And we'll look at that in a second. Total fertility rate is it's the number of births a woman is expected to have during her reproductive years. An individual woman is expected to have during her reproductive years. We calculate this by dividing the product 5 times the age-specific fertility rates by 1,000. And I'll show you why we do that. So the age-specific fertility rate is the births in a given year to women of a given age stratum. We use these different strata here, like for instance 15 to 19, 20 to 24, etc. So if we wanted to calculate the births in this given year, well, it's really it's a 5-year period, and that's why we end up multiplying it by 5, as you'll see here in this part of the equation, multiplied by 5, because this is a 5-year period. So for instance, if you have, this is in Egypt from 1997 to 2000, you had 764 live births from a total of 14,893.2 women of it ages 15 to 19. Again, this has to be women of reproductive age. So that's where we get this age-specific fertility rate. So we divide 764 by 14,893, right, 0.2, right? And then multiply that by 5 in order, multiply that by 1,000 to get the age-specific fertility rate per 1,000. And we use the sum of all of these. So we're saying this simple sigma means to summate. So we're summating across these different strata here to get the total fertility rate. A total fertility rate of 2.1 is considered a replacement fertility rate. So that's how many live births a woman would have to give in order to replace herself, because it's taking into account that you also have infant mortality. I don't know what a 0.1 of a baby is. Maybe it's a finger or something like that. Just kidding. But yeah, that's how we would do this calculation. So let's actually practice it. Now I'm going to use Excel for this calculation. I'm going to use Excel. I like using Excel to do things. So here's an example of how we would calculate it. So we have each age stratum. So what you could do in a situation like this is you can take the table, if you're given a table, like say this table, you can copy it and then paste it into Excel, and that would get you started with what you want to do, right? You can do that. Oh, so here. So this is a replica of the table that I have here. These are the different age strata. Here's the number of live births, and we need the age ASFR, right? ASFR, age-specific fertility rate, right? ASFR, okay, so to calculate that, we use the equation that I showed you before. And in Excel, you could write out the equations in this little area here. So according to the equation, we divide the number of live births by the number of women of that reproductive period, age period, and then we multiply it by 1,000. So let's do that here. To initiate an equation, you have to hit the equal sign, so that gives you this window for writing the equation. And here, you can either write it directly in the cell or up here, whatever you find more convenient. And we want to divide the number of live births, which is 764, and that's in cell N7, right? It's N7, by the number of women at mid-year, right? So this is that quotient, and I'm going to multiply that by 1,000, because that's what I was told to do to get the number of live births per 1,000. So I multiply that by 1,000, and I hit enter, and see that'll give me this age-specific fertility rate here, right? Same as this one up here. Now I need to do that for each of the strata. Instead of retyping that equation in for each of the strata, if I just grab that little corner, see that little box in the corner there? I grab it and drag it down, it'll repeat it for each of these cells. So I get all of the age-specific fertility rates. Now, so that'll give me what I want to this point to get the total fertility rate. And total fertility rate is the sum of the age-specific fertility rates times 5 divided by 5, because it's a 5-year period, right, for each of these strata, right? 15 to 19, 15, 16, 17, 18, 19, that's a 5-year period. So we're going to multiply those and then divide it by 1,000. We divide by 1,000 to get rid of this initial 1,000 that we had up here. So let's do it. Let's do it. All right, so I have to summate all of these values, right? So now in Excel, if I hit the auto sum, that should do what I want, right? And click. And so you'll notice it highlights the area that'll be summed. You always have to make sure that you're summing across the right amount of elements, right? But that's not all, because this number is too big. You see, I've already calculated here, and these two are not the same. So let's look at the equation again and see what else I have to do. So in addition to what I did, we have to multiply this. Oh, we have to multiply each of these by 5. Okay, multiply each of these by 5, and then, well, it's the same thing. So multiply by 5, and then divide by 1,000. So let's do that. Let's go ahead and multiply by 5. So I'll show you how I did it here, right? I did the same thing here. So I multiply. The universal symbol for multiplication is an asterisk times 5, and then I have to divide by 1,000, right? That's what I did here. I divided by 1,000, right? So multiply 5 and then divide by 1,000. And there we go. So what I did was I entered this equation into this little box here, and I was able to calculate my TFR. By the way, the general fertility rate, just the fertility rate itself, is just the number of live births across women of reproductive age divided by the total number of women through the reproductive ages. And in this case, there was total, well, actually, I can just get the number of live births by summing across these, hitting enter. So that's the number of live births. And then the number of women of reproductive age, do the auto sum and hit enter. Great. And then now I want to get, so here I give you the TFR, right? Total fertility rate, TFR, and then here is this general fertility rate. It's merely the quotient. So again, I hit equal. I divide 7101 by this number, okay, and then I did multiply it by 1,000, so I get it per 1,000. So I always like to put this in parentheses just to make sure I don't have any problems anywhere. And times 1,000, and there we go. We got 111.406 per 1,000. They match. Okay, so that's the start to what we're doing here. Next topic I want to cover is years of potential life lost. We have an issue with death, of course. We study mortality. We talk about death in terms of mortality rates. When we do that, we ignore what actually we lose when somebody dies. It's not just that a person is a one less member of the global population or of our nation's population. We lose a lot of potential life when somebody dies. And that depends, of course, when the individual dies. This became very intriguing to me during the midst of our coronavirus crisis, because people were saying, oh, an old person dies, well, who cares, right? You know, they're getting older anywhere. It's not affecting young people as much. So people were making this argument that they didn't have to get vaccinated, they didn't have to wear masks because, they're not as much of a risk as senior citizens are. Well, in terms of the risk, that is most likely correct because the majority of deaths have been among older individuals, vast majority of deaths with the coronavirus. However, sometimes it's not that a person dies when they're old, it's how much more they could have contributed before they died. And in many cases, people who died of this virus or die of other situations have comorbidities, so comorbid conditions that hasten their death. However, if they didn't get the virus, SARS coronavirus 2, in this case, they may have lived many more productive years, or even if it's just 2 more productive years of life where they could have accomplished something, written a book or something like that. So when we just look at mortality rates, we ignore the years of potential life loss. So this is what the YPLL does, is it accounts for years of potential life lost. And we have these statistics for our states. Like here you can find, if I can get this link to work, you can get the years of potential life loss for states like Pennsylvania and our different counties where we have the worst YPLLs. This is interesting though because we have YPLLs based on county, based on in terms of a Z-score. If you don't know anything what a Z-score is, a Z-score is a score that's based on a standard normal distribution where 0 is the average, and then like this 1.15, Z-scores are in standard deviation units, so this is 1.15 standard deviations below the mean, the state mean. So these people have lost fewer years of potential life loss versus, say, somebody like Cambria County, they're almost 2 standard deviations above the state mean. Standard deviation, hopefully you know this, I know people who took stats with me, we have 68% of all population values are between plus or minus 1 standard deviation from the mean. 2 standard deviations of the mean, plus or minus 2 standard deviations from the mean, encompass 95% of all population values. So for a county that has a YPLL at about 2 standard deviations above the mean, that represents half of 95, so it's 47.5% higher than the mean, right? So that's an incredible loss of life. So people are dying young over here. And then we also have this divided by race and ethnicity. It's very interesting. So let's see if we can find Philadelphia. My computer's kind of functioning really slowly right now. Yeah, Philadelphia is actually 1.53 standard deviations above the mean. All right, so interesting stuff to look at. I guess maybe they wanted me to accept the cookies. I am hungry for cookies, but I guess those aren't the cookies they're talking about. So what we're going to do is learn how to calculate YPLL. A lot of calculations, though. I told you once we got to the first part of the course, there's just a lot to do. All right, so here's an example of how we calculate the YPLL. We take the life expectancy, and the life expectancy can be whatever we want it to be. Like in this case here in table 2, I have it at 79 years. It can be 75, it can be 80, whatever one believes it is. You subtract from the life expectancy the midpoint of an age grouping or stratum. There's always a strata, right? We're always doing strata here, right? And then you multiply that. So this gives you the potential. So this is for individuals who are between 30 and 34. Somebody dies in this period, right? But the life expectancy is 79. The difference between those two will give us the years of life lost, and then we multiply it by the deaths in that age range, right? So that this is kind of a simple calculation. You're just accumulating how many deaths are lost within each of these strata. But because this stratification is based on this 5-year, right? This 5-year period here, and we want to get the midpoint, we take the minimum age, for instance, this case, the minimum age is 30. You add the maximum age of this stratum, which is 34. Then we add 1. We add 1 because we start at the first year of life going from 0 to 1. So we're not going to add 0, we're going to add 1 year to that. So we always have to keep that 1 in account. We always have to add 1 to these counts. Divide that by 2, so we get this average. Then we find the life expectancy. We subtract to get the difference, right? That's right here. And then we take the number of deaths. Population is actually not important here. I just probably put it in there because I did. We get our age-specific years potential life loss for each of these, and then we accumulate them. We add them together to get the YPLL. So let's fill up this table here. Again, let's go to my buddy Excel here. So in Excel, we have everything we need again. So this is a copy of that table. The only difference I did here, and by the way, you can use Excel when you do your exams. Now I'll ask you to fill in values, show me that you know what you're doing, but Excel is great for this kind of stuff. I want you to learn how to use Excel so you can be a master at it. So here's our question. We have the age 30 to 34, 35 to 39, 40 to 44. Usually we have more than that, but hey, this is what I'm giving you right now for this, just to learn how to do it. So we need our midpoint age. Now notice that I broke this up into 30 to 34 just because it makes it easier to work with Excel. So I can throw in the equation. So I have 30, 34, 35, 39, 40 to 44. So here's my equation. And again, when I write out an equation, so let me actually do the same thing I did before. Copy this. Let's put it right here. Okay. And let's empty some of these cells. Okay, cool. All right. So to calculate the midpoint of each of these strata, I have to simply take the lower minimum or the minimum and add the maximum to it, and then add 1 and then divide that by 2. So let's do that here. So again, I start by, whenever I want to enter an equation, I hit equal, and either I can write my equation in this cell where I actually want the answer to be, or I can write it up here. So let's just do this. So I need to take the minimum. It looks like a frowny face. The minimum is in cell A5. I'm going to add to that the maximum value. Now I'm going to add to that 1. And I'll close that out. I divide that by 2, right, and hit enter. So I get 32.5. So I want to do the same for the next 2 cells. So I can drag this down. There you go. So you see these are equal. Years to life expectancy. I think I said it was 79, right? So that's an easy equation. Hit equal. We'll take 79 and subtract from 79 whatever my midpoint age is. So notice that I have an actual constant here, and then I have this. This is a variable because it's going to vary. The cell level varies. Hit enter. Get 46.5. Let's see if this should work fine. Should work fine because I have a constant there, right? For the midpoint age. Everything else filled out because I set it up to fill out. Let's see. I said population is irrelevant. Let me just erase all this stuff so we can do it from scratch. So I need the age-specific years potential life loss. So this is, we know how many YPLLs we have here. There's 46.5. So this is going to equal 46.5 times 96. So we had 96 losses, right? Number of deaths. We get 4464, see that? And then again, we can drag down because we're just repeating everything for each of these calculations. And last but not least, the cumulative. Well, this is a little bit different. So the first value is going to be the same as this because we've only accumulated 44, oops, stop that, sorry. We've only accumulated that many deaths, so I hit equal, and I can just highlight this cell and say equal. But the next one is going to be the sum of these 2 YPLLs, right? So this is like me doing my budget. This is the way I do my budget every day, right? Take the value that's here, and I add to it the value that's right here. Right. So yeah, so now I can repeat from this point forward, and everything will work out. There you go. So according to this for these three strata, we have a total of 15,036.5 years of potential life loss. That means because of these deaths, and here we had a total of 371 deaths in these three age strata, we have a loss of 15,036.5 years of potential life that people could have done contributing more. So if we have deaths at an earlier age, the greater the YPLL. So we'd like to prevent that, of course. And again, like I said, when people die older, we end up having the lower YPLLs, but that doesn't mean that their deaths are meaningless. They still could have contributed a lot to this world. Think about people like Betty White, who died recently, who contributed a lot all the way to the end. You never know what a person can do, so that's why we don't take that for granted.